G'day and welcome back to Mathematics for a new integration video. Sorry, I've been pretty absent recently. I've been moving house and life has just been hectic, so I've had no time for my little hobby. But now I'm back, hopefully back to putting up a new video every week in the lead up to some assessments coming up for my students. Okay, starting off where we picked up last time with Integration Guide Part 1, now we're going to Part 2. Today we're focusing on integrating exponentials, logarithms, and trigonometric functions. Before we do that, we'll just do a quick recap of how to differentiate exponentials because that'll be helpful. So first one is differentiate y equals e to the x minus e. If you have no idea how to do these, I recommend going back and watching my differentiation guide where I ran through how to differentiate all of these terms. Okay, so first one, the derivative of e to the x is itself, e to the x. And e without a power is just a number. It's like 2.7 something. And the derivative of a number is just 0. So the first one is just e to the x plus 0. For the second one, when you're differentiating an exponential but the base isn't e, the exponential term is going to stay the same, but the extra step is to multiply by ln of the base. So in this case, our derivative would be 7 to the x, remaining the same, and then multiplying by ln 7 because 7 was the base. Okay, and for C, differentiating e to the 4x minus 1, the exponential term, as always, is going to remain unchanged. All we need to do is multiply by the derivative of the power, which in this case is 4. That's why our answer is 4e to the 4x minus 1. Okay, splendid. Now we remember how to differentiate. Let's try and work backwards and do some integrations. So since e to the x is its own derivative, it makes sense that e to the x is its own antiderivative, and that's why the integral of e to the x is just e to the x. Don't forget your plus c or your only 10 push-ups. For the second one, when your power has a constant like e to the ax plus b, if we were differentiating, we would be multiplying by the derivative of the power, which would be a. So because we're integrating, we're going to do the opposite, and we're going to divide by the derivative of the power, which is a, and of course plus c. And for different bases, with the differentiation from before, we were multiplying by ln of the base. In this case, we're doing the opposite as always, so we are dividing by ln of the base. Keeping the exponential term the same in all three scenarios. So the exponential term is never going to change whether you are differentiating or integrating, and that's really important to know. Let's do a few examples. Here's the first one. We have e to the minus 5x plus 1. Okay, so integrating this, once again, I'm going to say this a lot today, it's going to get boring. The exponential term is not going to change. This is still going to be e to the negative 5x. If we were differentiating, we would multiply by negative 5. So because we are integrating, we are going to divide by negative 5 with a constant. So you can write negative 5 on the bottom. You can take the negative out the front if you like. Either of these are completely valid answers for the antiderivative of e to the minus 5x. On to the next one. We have the integral of 5 to the power of x. So using the result from before, the 5 to the x is going to remain unchanged. But this time we need to divide by ln of the base. So divide by ln 5, which looks like this. And of course, plus c. So quick, easy result, but just to be aware of how you integrate when the base is an e. Most of the time it will be e, but sometimes they'll throw a curveball like this at you. And there'll be a reminder of this on your reference sheet if you are feeling forgetful. Okay, next one, a bit more spicy. We've got e to the 2x plus 1 over e to the 2x. So e to the 2x is already in index form. It's ready to go. To integrate 1 over e to the 2x, we need to write this in a different form. We need to use negative powers and write this as e to the minus 2x. Now we're ready to integrate. Both of these terms are exponentials, so they are going to remain unchanged. We just need to divide by the derivatives of the powers. So derivative here is 2 and derivative here is minus 2. So we'll keep them the same, divide by 2, divide by minus 2, and add your constant. There is your answer. If you want to make it look a little bit more extra, you can factor out a negative 1/2 or a 1/2 out the fronts, but these are both valid answers, both worth full marks, as long as you got that plus C. Okay, if that made sense to you, you are encouraged to pause and try these two by yourself. Question B has limits, but apart from that, it's very similar to what we just did. Or if you can't be bothered and you want me to do it, here we go. Okay, first one, e to the minus x integrates to e to the minus x, but we are going to divide by minus 1 because that's the derivative of the power. If I say it 400 times, you might remember it. And 3 to the x is going to remain as 3 to the x, but we are going to divide by ln 3 because the base is different. The base is not e. So there we go, e to the minus x divided by minus 1 minus 3 to the x divided by log 3 with a constant. I can't remember if I did anything more with that. Oh yeah, dividing by -1 is just putting a negative out the front. So you can make it look a teeny tiny bit better if you like, but again, both valid answers, both worth full marks. Okay, over on the right, similar ideas, keeping our exponential terms the same, but we are going to divide by the derivatives of the powers. So we're going to divide this one by 4 and divide this one by 2 to obtain this result. That's the calculus done. Now we're going to substitute in x equals 2 and then subtract x equals 1 subbed in. So when we sub in 2, we get 4 times 2 is 8 plus 1 is 9, and we get 4 here. So there's the 2 subbed in, minus subbing in 1, we get powers of 5 and 2. There's not much more we can do with this. We could put it all into a calculator and get a decimal if we were feeling disgusting, or we can just expand it out, and then if you want, you can combine the 4s and the 2s into single fractions, but again, not much we can really do here in terms of making our answer better. We could factor out e's and make one fraction, but honestly, who has the time? Not me, it's a Saturday. Let's keep going. Okay, looking at some HSC style questions. These two-parters are really common in assessment scenarios. We've got part 1 is differentiate, and then if you've done part 1 correctly, part B is a scary looking integral that's meant to be made much easier by doing part A. Okay, starting off with A, we have x times e to the 3x, and we are differentiating. So because we have a product, because we have x times e to the 3x, we're going to use the product rule, which I have videos on if you are a bit rusty. So here goes our product rule. We're going to differentiate the x first into a 1, leave the e to the 3x alone. Then we're going to plus, leaving the x alone, and differentiating the e to the 3x to 3e to the 3x. Okay, doesn't matter what order you do these in because there's a plus in the middle, but I like to start differentiating here and then differentiating here. Okay, there's the calculus. Let's simplify it. Let's just write e to the 3x plus 3x e to the 3x. And now question B actually gets a bit easier if you factorize your answer. So we can see here we have a common factor of e to the 3x. Factor that out the front and you get 1 plus 3x as an even better final answer for part A. So well done if you got that as well, or it just makes sense, you're doing well. Okay, now we have the derivative. Let's try part B, where we find the antiderivative of e to the 3x times 3 plus 9x. So how is this question related to our answer from part A? Well, they look very similar. We've got an e to the 3x, but our bracket we can see has been times by 3 because 1 and 3 have turned into 3 and 9. So we are just trying to make our question look like our answer from part A because we know what the antiderivative of this is. It's where we started. It's x e to the 3x. So what we're going to do is we're going to take the 3 out of this bracket and just yoink it out the front of the integral like this. So 3 factored out, put it out the front because now the inside of our integral perfectly matches our answer from part A. So integrating e to the 3x times 1 plus 3x, we know what that anti-differentiates to. We go back to the start and it's going to be x e to the 3x. So remember, integration is just differentiation in reverse. So that's usually quite helpful. So our antiderivative is x e to the 3x. We're subbing in a 2, subbing in a 0 with a 3 out the front. So the 0 just turns into nothing, thankfully. But the 2, we get 2e to the 6 and then multiply that by the 3 out the front and we get 6e to the 6 as our final answer. All right, moving right along. We got a lot to get through. This next one's from 2018. It's a band 3. Hopefully this stuff is making sense because this one is your first lot of homework for today. I want you to try this integral by yourself. Post your answers in the comments and I'll validate you by telling you if you're correct. If you're wrong, I will bully you. All right, moving on to the next one. Another HSC question. This one's more recent. It's from 2020. We've got a band 3 part and a band 5 part. Again, very similar to what we just did. Part A, differentiate, and then if you've done that correctly, part B is meant to be pretty easy. So let's start off with part A. Oh, sorry, spoiler. We're going to differentiate this once again using the product rule. You can expand if you want and then do product rule, but it's just easy to do product rule. So product rule looks like this. Differentiating the e to the 2x to a 2e to the 2x, and then leaving the 2x plus 1 alone. That's in green. Plus, for the second part, leaving the e to the 2x alone, and then differentiating the 2x plus 1 to be a 2. So there's our answer. We need to simplify this a fair bit for it to be useful in part B. So we're going to write our answer a bit more simplified like this. Now we're going to expand it out and we're going to say this is going to become 4x e to the 2x at the front and then 2e to the 2x when you multiply by 1. The reason we expanded is because now we have like terms. We have e to the 2x's that can group together. And so this becomes 4e to the 2x. And now we once again can factorize because like the last question, it's going to make it more simple to do part B. So common factor of 4e to the 2x. Take that out the front and we get x plus 1 as our other factor. And that's our fully simplified, fully factorized answer for part A. And that's probably the band 5 part, because now that we've done that, the next part is meant to be pretty straightforward because we're trying to integrate x plus 1 e to the 2x, and we have the antiderivative of 4e to the 2x times x plus 1 because that was the question. So we know this integrates to this. So how can we make this look like this? Well, we just need a 4 here. We can put a 4 there by just putting a quarter out the front because a quarter times 4 is just 1. So it's all perfectly legal, Your Honor. Okay, with the 4 in there and the quarter out the front, now the inside is going to integrate to the question from part A, which was e to the 2x times 2x plus 1. So there's our integral. We've got a quarter out the front and we've got a plus c on the end. And there's our quick and easy 1 mark if we did part A correctly and flawlessly. So there we go, 2020 HSC. Not too bad if you know your stuff, as we say. Okay, on to the next part. Let's look at how we can break the rules of integration and then work around them. We're going to start by integrating 1 over x squared, which we've done on this channel before. We're going to write that as x to the power of minus 2, raise the power by 1, divide by the new power, and then plus c to get our final answer, negative 1 over x plus c. Okay, that was great. That worked flawlessly. Let's try that again with the integral of 1 over x. Let's write it in index form as x to the power of negative 1. Now we'll apply our rules again. We'll add 1 to the power and divide by the new power. And we have a problem. We cannot divide by 0. So this is clearly not working. And so it seems like this doesn't have an antiderivative until you get that light bulb moment, that flashback, and you remember that 1 over x is actually the derivative of log x. Okay, so in some scenarios, fractions you can integrate just by using good old-fashioned integration and powers, although sometimes you need to use a logarithm, and being able to spot these is a really important part of being an integration pro in the advanced maths course. So here are our results. The integral of 1 over x is equal to log of x with a constant. For these ones, we're going to be putting absolute values around our x's or our functions because logs are only defined for positive values, so we're only integrating over a positive domain. That's the short version. The long version for why there's absolute values here is a rabbit hole I don't want to go down because this video is already probably going to be like 30 minutes. Okay, and similar scenario, when you have a fraction and the bottom of the fraction is a function and the top of the fraction is a derivative of the bottom, this is again a scenario where we can apply a logarithm and do ln of absolute value f of x plus c. Okay, that's because if you differentiated log of a function, you get a fraction, as I covered in a previous video. So these are the results we're going to be using for the next 10 minutes. Let's dive in and see how they work. Here's our first one, 2 over 3x integrated with respect to x. All right, for this one, 2 and 3 are constants. So as always, if it makes your life easier, just put your constants out the front of your integral, because now we have 2/3 integral 1 over x dx, and we know that the integral of 1 over x is log x. So it's 2/3 of log x, absolute values, and a plus c. Quick and easy if you know your stuff. If you know what this integrates to, it's a very straightforward question. Okay, a bit of a spicier one. A fraction. On the bottom we have x cubed minus 3x. On the top we have x squared minus 1. So let's see if we can apply a logarithm. For it to be a logarithm integration, we need to have the top being the derivative of x cubed minus 3x. Now the derivative of x cubed minus 3x is 3x squared minus 3. So it'd be great if the numerator was 3x cubed minus 3, but currently it's only 1x cubed minus 1. So we need to multiply the top of the fraction by 3 to make it match the derivative. If I'm going to multiply the top by 3, I need to put a 1/3 out the front of the integral so that it keeps the balance. So 3 on top, 1/3 out the front. Now the top is the derivative of the bottom, and now we can integrate using a logarithm. So we have 1/3, we have natural log of the denominator with absolute values with a plus c. So lots of stuff to remember. 1/3 out the front, log, absolute values, denominator, plus c. Okay, takes a while to get good at these. If you're brand new, you've got to be patient. You've got to keep trying. Okay, but if that was making sense, you are of course encouraged to pause and try these ones by yourself, because I'm going to run through my answers and you can see if we match, or maybe you just want to watch me do it. I can't control you. I am very far away and talking to myself in a spare room. Okay, first one is the integral of 1 over 2x minus 3. Using a logarithm, the derivative of the bottom is 2, so we need to make the top equal to 2 so we can apply a logarithm. So put a 2 on top, put a half out front, and now it's all balanced. Now we can just do a half out the front, natural log of the denominator with an absolute value with a plus c. Beautiful, it's clicking. Over on the right, using logarithms again, the derivative of the bottom would be 3x squared plus nothing, so just 3x squared. So once again, same trick, I'm going to put a 3 on the top and a 1/3 out the front like so. Now we can have a 1/3 out the front with a logarithm of the bottom, but this time we have some limits. So we have natural log of x cubed plus 1 in an absolute value. All we need to do is sub in 3 and sub in 1 and subtract them. So when we sub in 3, we get 3 cubed is 27, plus 1 is 28, and the absolute value of 28 is thankfully 28. These are pretty much always going to be positive values, so the absolute values don't really matter, but it's nice to include them in our answer anyway to show that we know what we're talking about. When we sub in 1, 1 cubed plus 1 is 2, so we get this result here. We can tidy this up because when you do log minus log, you can combine these together and do log of a divided by b. So we can write this as log of 28 divided by 2, which is log 14. So 1/3 log 14 is probably our best simplified answer. Stunning, magnificent, moving right along. Okay, finishing off with a challenge for this section. We're integrating tan x with respect to x, which is confusing because the integrating trigonometry is the next section. We haven't got up to it yet. So it seems pretty tough until you recognize that there is another way that you can write tan. Tan can be written as sine over cos. Why do we care? Well, friend, because the derivative of cos is negative sine. So by writing tan as a fraction, we've actually transformed it magically into a question that we can sort of do using logarithms. So to make the top the derivative of the bottom, all it needs is a negative. So easy peasy, negative on the top, negative at the front, and then it's all balanced. So the top is now the derivative of the bottom. So we can just integrate it to minus log of the bottom plus c. Boom, done. Very cool. All right, what are we doing now? I forget. Okay, here's a question from 2011, which was my HSC. I can't remember if we're actually doing this one or if this is homework. Let's see. We're doing it. Okay, cool. Band 4, starting off with the integral of 5 over x. So, like I say, if it makes your life easier, put constants out the front and write it as 5 integral 1 over x dx. Okay, integral of 1 over x, as we have covered to death, is the natural log of x. So we have 5 outside of log x. I forgot the absolute values. It doesn't matter, but you should be better than me and do the absolute values. Okay, top limit is e to the 3 and bottom limit is e. So subbing it in looks like this. Now, when you do log base e of e to the power, because these two operations are inverse, when you apply them to each other, they cancel out. That's why log of e is just equal to 1. And with this one, the log and the e cancel out, bringing the 3 down. So this just really turns into 3 minus 1, okay? And you can check that with the calculator if you're really not sure with your logarithms. Anyway, we get 5 times 3 minus 1. 3 minus 1 is 2. And then 5 times 2 is 10, of course. And so there is your 2-mark answer from a 2011 Band 4. My HSC exam, happy memories. Okay, I think we're going to do this one as well. This one's from 2019, Band 3.5, typical HSC style question. Part I, differentiate. Part 2, integrate. All right, let's stop dilly-dallying and get into it. Differentiating the square of log x. There's 2 ways you can do this. You can write this as log x times log x and do product rule, or I'm going to differentiate how I normally differentiate a bracket to a power. I'm going to use the chain rule. So chain rule says, power comes down, reduce the power by 1, and now multiply by the derivative of the inside of your bracket. The derivative of log x is 1 over x, so I'm going to multiply by 1 over x. And now we're just going to write this as 2 log x over x by combining it into one term. Okay, very cool. So the derivative of log x squared is 2 log x over x. how does that help us do part B? Well, the integral of log x over x, let's make it look like our answer from part A. Let's put a 2 up top by putting a half out the front. Now it matches. We know what this integrates to. It goes back to the start and goes to log x being squared. So integrating the inside to log x squared, don't forget your half out the front, and don't forget your plus c. And there is a quick and easy 3 marks if you know how to differentiate logs, if you know how to do the chain rule, and you know how to use your eyes and just see, oh, they kind of look the same. Let's make them the same. Anyway, the reason I'm showing a lot of these is because they're very common, and like if you can just quickly spot the link between this answer and this question, they're really, really straightforward and easy. So I like to cover a lot of these. Okay, on to trigonometric integration for the last part of the lesson. How long have I been going for? About 6 hours. Okay, this is only going to make sense if you looked at my lesson on differentiating trig. So if you haven't, please go back and watch that, because otherwise this is going to be nonsense. But in that video, I explained that the derivative of sine x is cos x, which means the integral of cos x is sine x with a constant. The integral of sine x with respect to x is negative cos x, because it's negative cos when you differentiate becomes sine x. And we also looked at earlier that the derivative of tan is equal to sec squared. So the integral of sec squared is equal to tan. So these are our 3 results we're going to be applying today. Here's a little memory tip to get this burned into your brain pretty quickly. I like to draw a little circle diagram, S, C, negative x, negative c. And the blue lines are me differentiating, and the red lines are me integrating. If you're looking for a new tattoo, I would recommend this, because if it's on your body, then how's NASA going to stop you from bringing it into your HSC exam? So play smart. Okay, so S, C, negative x, negative c. Blue arrows going clockwise for differentiating, and red arrows going anti-clockwise for integration. Drawing this diagram in your exam booklet can help you save some time thinking about, oh, does sine go that way? Does cos go that way? Here's your cheat sheet, basically. So write it down. Okay, what happens when you have cos, sine, or sec squared of an angle with a constant inside, like a, for example? When we were differentiating, we would be multiplying by the derivative of the angle, which in this case would be a. So for now, because we're integrating, we are going to divide by the derivative of the angle, which in this case is a. So same result, but in this case we have 1 over a, or a divided by a, whatever you prefer to think of it as. All right, enough yapping. Let's do some calculus. First one, 3 times sec squared 5x dx. All right, constant out the front, goodbye. Okay, sec squared integrates to tan. We have an angle which is 5x. The angle is never going to change. The angle are kind of like exponentials. They are going to remain the same throughout all your working. However, in this case, we need to divide by the derivative of our angle. So derivative of 5x is 5. So we have 3 out the front. We have sec squared integrating to tan. Angle remains the same. Dividing by the derivative of our angle. That's why there's a 1, 5 out the front, or you can do the whole thing over 5 if you prefer. It's your life, you live it how you want. Don't forget your plus c, and then 3 times a fifth is 3/5, and there is our answer. Okay, any questions? All right, moving on. Next one, integral of cos of pi minus 2x. Okay, we know cos from our tattoo. Cos integrates to sine. So this thing's turning into sine. Look at that, the angle's not changing. Like I said, the angle never changes. What we need to do is think about what the derivative of our angle is and divide by that. The derivative of pi minus 2x would be minus 2. So we're going to divide by minus 2. Again, do it as a big fraction if you want. I don't care, it's your life. Plus c, don't forget. I think that's all. Yeah, put the negative at the front if you care, whatever. Anyway, there's our answer. Calculus, this is fun. All right, example 3, integrating sine, 2 out the front, and then we've got a 2 pi x over 3. All right, so let's think. 2 out the front, why not? Put the 2 out the front. Okay, so sine integrates to negative cos, I believe. It does, yeah. So we're changing this to negative cos. We're keeping, oh God, what a mess. We're integrating sine to cos with a negative. The angle is not changing, like I said, all right? You gotta listen, the angle's not changing. But we need to divide by the derivative of the angle. The derivative of 2 pi x on 3, this is just a constant times x, and the derivative of that will be the constant. So dividing by 2 pi on 3, this is a bit of a mess. You can actually just put this whole fraction into your calculator if you want, but the fun way is the 2's are cancelling out, the 3 is going to flip up top, and so we just get negative 3 out the front with a pi on the bottom, sorry. So 2's cancel out, 3 goes up top, Pi's still there, negative's still there, and there's our slightly better looking final answer for the integral of this mess. Okay, your turn if you choose. A little bit of homework. Try these ones by yourself. Compare them with my answers, which are coming in 3, 2. Now, all right, so sine integrates to minus cos. So 5 sine integrates to minus 5 cos plus c. Simple as that, okay? Because the angle was just x, we don't need to do anything because we're just going to be dividing by 1. So why waste your time? Over on the right, cos is going to integrate to sine. But why is there a 1/3 there? Oh, because we've divided by the derivative of the angle, which is 3. And notice how the angle hasn't changed? That's important. People make that mistake. So cos to sine, angle the same, divide by derivative of the angle. Limits are pi on 2 and 0, so we'll chuck them in. Put the 1/3 out the front for now, because we don't care about it. We're going to put that in later. Sine of 3 pi on 2, what's that? Sine of 270? Let me think about my sine graph. I think that's -1. In fact, I'm pretty confident it is -1. Sine of 0 is just 0, so we get -1 plus 0, which is -1, so we just get -1/3 as our answer. Okay, I feel like this was too much for one video, but I've already committed, so I'm just going to finish it. Okay, some more your turns, but really just my turns because I'm going to do them anyway. Okay, sine integrates to negative cos. There's going to be a 4 there. The angle's still going to be x over 2, but we need to divide by the derivative of x over 2, which is a half. So sine becomes cos with a negative. 4, still chilling. Angle, still chilling. Divide by derivative of the angle, which is a half. And don't forget your plus c, or you got to give me 10 push-ups. The half, or the 2 on the very bottom, is going to flip up top because 4 divided by a half is 8. So we end up with -8 cos x over 2 plus c. Okay, on the right, we got some more limits. We know sec squared integrates to tan. 2 is going to be chilling there. The angle's still going to be 2 pi on 6, but we need to divide by the derivative of the angle, which is 2 pi. So sec squared goes to tan. 2 out the front if you like. 2 pi on x, still 2 pi on x, but I've divided by 2 pi like I said I would. I'm a man of my word. We're going to put that 2 pi out the front for now, subbing in an 1/8, and we get 2 pi over 8. Subbing in 0, we just get 0, which is very merciful because tan 0 is nothing. A little bit of ASMR mathematics for you. Okay, tan 2 pi on 8, that's going to be pi on 4, which is 45. Tan 45 is equal to 1, that's the nice one. So we have 1 over pi out the front, multiplied by 1 minus 0, which is just going to be 1. So we just end up with 1 over pi. There we go. That was fun, wasn't it? Yeah, I had fun. Okay. Up next, a couple of HSC questions that I am too tired to do. So you try these from 2014, band 4, bit of homework, post your answers in the comments, and again, correct answers get validation, incorrect answers get permanently banned from the channel. All right, finishing off with our last question. Thank Christ, I need to go for a walk. Band 5, 2019, multiple choice. Which of these is equal to tan squared x dx? Now, at no point today have I told you how to integrate tan squared. I showed you how to integrate tan using a logarithm, but this one is a pretty tricky question and it requires a very specific approach. All you need to know that a man and a tan is sexy, which is why I'm going to go for a walk to the beach as soon as I stop recording this. Where is it? There it is. A man and a tan is sexy. All right, this is one of our Pythagorean identities, and we can rearrange this to say that tan is equal to sec squared minus 1. Why do we care about this? Because sec squared and 1 are both things that we know how to integrate. So if we change this to be this, we can actually do some calculus. So we can write it like this. And then sec squared we know integrates to x, integrates to tan. 1 integrates to x, and then we're going to have a constant. So we end up with tan x minus x plus c. So if you did this yourself, or you cheated, and you looked it up, and you got the answer was option A, you're a genius. You're a band 5 certified genius. Congratulations. Enjoy your weekend. All right, thanks for watching. Hopefully that gave you some confidence in integrating more complicated expressions in the advanced course. And yeah, hopefully we'll have some more advanced content up soon, but going to be focusing on extension 1 for the next few weeks. But I'm rambling. Thank you for watching. Good luck on your calculus journey, and I'll see you in the next video. Goodbye.